Welcome to the last part or the part 5 of lecture 1. Here in this part, we are going to discuss some examples. So, we have taken a data set from R called empty cars data set, which we discussed at the beginning of this lecture, that we want to predict miles per gallon given certain features of a car. So we have taken one single feature of the car, the weight, and we taken the miles per gallon on the y-axis. We plot the data, and this is typically a regression line that we try to fit here. So how we fit this model? We will put it into a structural, matrix notation format. So this is my model MPG beta naught plus beta 1 WT plus epsilon. So we write the model in terms of linear models or in terms of matrix notation y equal to x beta plus epsilon, where y is mpg1, mpg2, mpgn in that is the first sample in the data set, second sample of the data set, and nth sample of the data set. The design matrix or the feature matrix will have first element 1 1 1 1. The second column will be the weight of the first sample, weight of the second sample, weight of the nth sample. So this gives me the design matrix or the feature matrix. Beta will be beta naught and beta 1. You can see beta naught and beta 1, and residuals will be epsilon 1, epsilon 2, epsilon n. Now if I set up the normal equation uh, and solve it, then what will happen? X transpose X will be basically n summation wti summation wti and summation wti square. I have to make the calculate the inverse of this matrix and then multiply the x transpose y, and x transpose y will give me summation of first element will be summation of mpg, and second element of the x transpose y will be the cross product of weight and miles per gallon. And you solve this, you calculate the inverse of this matrix and do this matrix in multiplication, then the resulting solution will be the solution OLS estimate of beta naught and beta 1. Now I want to consider horsepower as the feature and miles per gallon as the target, and just looking at the visualization looks like a simple straight line may not be a right one. Maybe a quadratic model is a right one. So I want to model it as a mpg plus beta naught plus beta 1 horsepower plus beta 2 horsepower square plus error. So technically we can do that. So how can we do that? So miles per gallon, this is my model, miles per gallon equal to beta naught plus beta 1 horsepower plus beta 2 horsepower square plus epsilon. So we want to write this model in terms of linear model like y equal to x beta plus epsilon. So y is miles per gallon 1, miles per gallon 2, miles per gallon n, the nth sample of the miles per gallon. The feature matrix of the design matrix, the first column is corresponds to the intercept or the bias 1 1 1. Second is HP. So the what is the first sample of the HP, second sample of the horsepower, nth sample of the horsepower. Then I'm creating a new column in my database. This new column is just basically square of this column, HP square, HP1 square, HP2 square, HPn square. And then I'm basically in the same linear model construct. So the linear model is effectively linear in parameter. As long as my parameters are linear, the model is linear in parameter, we have no problem. We can estimate these methods, use these methods to estimate the results. And same way we can use the normal equations to estimate the beta naught, beta 1, beta 2. So what is this tells us? This tells us effectively we can implement nonlinear regression using simple linear model and least square technique. Consider the ith record yi as a function of xi plus epsilon I, just one xi, and that function is represented as summation beta j equal to 1 to k beta j phi j x, and I can write it as a phi times beta, where phi is known as the basis system for fx, where phi j x are completely known to us. So for us, first phi 1x is 1, phi 2x is hp, phi 3x is hp square. So generic term for curvature in linear regression, so we can fit a polynomial regression like this: y equal to beta 1 beta 2x beta 3x square plus dot dot dot. So sometimes in machine learning, phi is known as engineered features, the basis, which is in functional analysis of the mathematical modeling, we call it basis functions. In typical mathematical statistics, we call it basis function, but in machine learning, we call it engineered features, and the process is known as feature engineering. You can model it if you have a sinusoidal kind of behavior. If you know that you're working with some voice recording, or some temperature data, rainfall data, which has a sinusoidal behavior or seasonal behavior, you can use sine cosine functions of an increasing frequency. So like y equal to beta 1 beta 2 sine omega x beta 3 cos omega x. In this way, you can define a function where omega is 2 pi by p. P is the period length of the period of the oscillation. And we assume p is known to us. Then phi, the basis function or basis, will be 1 sine omega x cos omega is sine 2 omega is cos 2 omega is. And beta will be basically beta 1, beta 2, beta 3. And you can again model it as a linear model format, and phi is your design matrix or the feature matrix, where your phi is known as the engineered features. So if you want, you can always try to model mpg as a function of beta naught plus beta 1 sine omega times hp or horsepower plus epsilon, and this will be known as the engineered features, provided you know the value of omega. This is also known as functional estimation or functional learning. We are writing the functions with its basis expansion y equal to phi beta, and let's assume the basis of the engineered features phi are fully known. The problem boils down to beta is unknown, and hence how to estimate beta. So we typically fit the regression line miles per gallon as a function of horsepower. Now if you put the horsepower squared, the quadratic term, into it, then basically what is happening, your data is in two dimension. The original data is in two dimension because you have miles per gallon and horsepower, so original data is in two dimension, but you add a new dimension. So you your data is in two dimension, but by adding a new feature, you are basically putting your data into higher dimension. Initially I had my data in two dimension because horsepower is one dimension and miles per gallon is another dimension, so original data is in two dimension. But now by putting a horsepower square, I am putting the two-dimensional data into three-dimensional model or three dimensions. So I'm putting my data into higher dimension. I am trying and in hoping that in the higher dimension I will fit a linear hyperplane. So I will fit a regression plane, two-dimensional plane on a three-dimensional cube, and that will model the relationship between horsepower and miles per gallon nicely, and this is what is known as feature engineering. With this, I'm going to stop at the first lecture. In the next lecture, we will discuss sampling distribution and inference of regressions. Thank you very much for your time.